Hello, everyone. The broadcast has started, and I'm going to start the webinar soon. Okay. Okay. So this webinar is on the lesson Temporal Difference Methods, which was uh, which was to be covered and read in this week. I'm sure many of you have gone through it, and I've understood the concepts, not very complicated. And in this webinar, I will discuss some of the key points of this lesson, and I will also go through some of the quizzes. What's the difference in the quizzes? And if we have time, I can go over the coding workspace as well, the coding of the coding assignment. Okay, so let's start with our webinar. So so why do we need temporal difference method if we already have Monte Carlo method to to compute the action value of a state action pair? So the whole point of these two methods is to update the Q table that we saw previously in MC method lesson. So there is a Q table that you update, and the intention behind that is to come up with an optimal action value function. And the action value function then can be used to decide an optimal policy for any environment. So the point of these two methods is to update the Q table and generate an optimal action value function. So why temporal difference methods if we have MC methods already? So for Monte Carlo methods, you have to sample an entire episode before you update any action value of any state action pair. Now that is not feasible in all the tasks. It is not possible for all the environments. For example, autonomous car driving. If you are writing a model, writing an algorithm which which is used for autonomous car driving, and you want to write a function that is going to compute the action value of a given state action pair, and to compute the optimal action value function, you can't use MC methods because MC methods waits for whole episode to end, and in this case, the end of the episode is that the car is crashing somewhere, right? So the episode terminates when the car crashes. Now this is not financially or even safety wise, it's not feasible. Uh, you can't wait for the episode to end. So what do you do? So for that reason, we use temporal difference methods. Temporal difference methods do not depend on sampling of the whole entire episode. It will update the Q values after every time step. That's the literally temporal difference means after every time step, every difference in time, you update the Q values. And why do we update the Q values again? Is to obtain is to compute an optimal action value function, which then can be used to generate an optimal policy. So let's, for next few slides, I will discuss more about the differences in these two. So let's move on. first of all, MC methods. So how do you update a Q value using MC methods? So suppose the current estimate for being in state 1 and taking action right is 6. And then the agent samples one whole episode. The episode terminates, as you can see here. The agent started with this state, took action right, and so on until it reached uh, this state 4 and got the reward of 10. Now, if the discounting factor is 1, the total return that the agent received in this episode for this state action pair, for being in this state and taking this action, is 10 minus 1 minus 1, that's 8. So you sample whole episode, get the new uh, return, and then you use that return to update this. So if you remember from last lesson, if the return from sampling a new episode was 8 and the current estimate was 6, we update it using either the incremental mean function, or we use constant alpha. So this will be updated to uh, difference between 8 minus 6 plus some alpha times the difference, and you add 6 to it. So this will be updated to 6.2 or whatever the value of alpha is. So the point is, for MC methods, you have to finish the whole episode before you update the value of this state action pair. And same goes for other state action pairs as well. On the contrary, for the TD methods, you do not have to wait for the entire episode to be over. As you can see here, the agent starts again in this state, takes action right, and then goes to gets a reward of -1, goes to next state, and select action right. Now these actions are selected based on the epsilon greedy function again, as you have seen in the previous lesson. So now the agent didn't complete the whole episode. It will update its current estimate of action value using the current estimate of next state and action pairs action value, that is 8. So this is one way to update the current action value of this state action pair. So the agent doesn't depend on the later states after state 2. The agent doesn't know what the final state was, and the agent doesn't care. The agent only cares about what the current estimate of state action, sorry, what the current estimate of the action value is for this state action pair. And then it uses that to update its current estimate. Similarly, if the agent started in this state and took this action and got into, say, state 3, and then selected action up, so the agent to update the current estimate of this state action pair would only depend on the state, uh, the action value of only this state action pair, the current estimate of the action value of this state action pair, and so on and so on and so on. Right. So, TD versus MC method. So again, I will summarize. Monte Carlo method depends on sampling the full episode, and then you update the action value of each state action pair using the actual return GT. This word is important, actual return, because this return was actually experienced by the agent when sampling this episode. On the contrary, in TD methods, one of those is SARSA 0, which we will know, which we will learn soon. So in TD methods, the agent doesn't depend on the actual return. It depends only on the estimate the the estimate of next state action pairs action value. So so when we saw in the previous slide, now this plus 8 is again an estimate based on the agent going into next state and action pair, going to next state and selecting some action. So even this was obtained from somewhere here, and now this estimate will be updated based on this estimate. So the key word here is actual versus estimate. In Monte Carlo method, the the returns are actually experienced, the rewards and returns are experienced, whereas in TD method, these are estimates, and the current estimate is updated using estimate of the next state action pair. And the important thing is that this is updated after every time step. You do not have to wait for the whole episode to end. That is the advantage of this method. Okay, again, so you will learn this later in the nano degree, but I thought it was important to mention it here. Now, suppose this is one sample episode. Okay, when you use MC methods, and suppose you sampled 3 full episodes using Monte Carlo methods, as you can see, they have very high variance. Now you will ask why, if the environment is same, why the the end the ends are so different, why are they so away from each other, is because when you run a full episode, there might be some random events happening in the middle of the episode. So in the beginning, most of the events are the same, but as you move further along the episode, when you use more time steps, there are some random events happening. So the random events that are happening here in this episode might not happen here and might not happen in this episode. And that's why, due to randomization, they can end up at very different points. And that's why MC methods have very high variance uh, in generating the action values. But they have low bias because it's perfect information. It's actual perfect information. You complete whole actual episode and you gain information about the action values from actual experiencing actually the whole episode. So it has high variance but low bias. On the contrary, TD methods have low variance because they do not go beyond one step, one next time step. They only depend on one next time step. They don't go beyond that. That's why the variance in the action values generated using TD methods is very low. But again, it's high bias because it is an estimate based on an estimate. As I mentioned previously, you update your current estimate based on the estimate of next steps action value. So it's more guessing and less accuracy. On the other hand, here in MC methods is no guessing at all, but due to randomization, they are very apart from each other. So you will ask where, how do I use these two in different places? So it depends on your model, what task you have. Um do you Is it a reflexive task, or is it a perfect information task where you have to know complete information about the whole episode before taking any action? In that case, you will need MC methods. Uh, on the other hand, if your task is reflexive, if you want to take actions right away, given current state, and you have to choose the best action, you use TD methods. So you will know more about the application of these two later in the nanodegree as well. How you use these two for different kinds of environments. Okay. So there are three ways of updating the action value of each state action pair after each time step. And these are the three ways. Starts 0. This is the most basic method. Starts max or Q learning. Same. They have two names. As you can guess, it refers to max of something. So we will go in more detail about this. Expected SARSA might be taking some expectations of some action values. You can guess. So these are the three methods. So let's go into more details of these three methods. Okay, SARSA 0. Now, now this is the update function for SARSA 0. Uh, it's very similar to Monte Carlo methods again, but the only difference is that this is an estimate and not an actual return. So the procedure of using SARSA 0 method uh, is as follows. So suppose you are in state 1, okay, and you have epsilon greedy policy to select your actions. So due to epsilon greedy policy, you select suppose action right. So you are in state 1 and action right. So this is your state action pair that you will update in this step. Okay. Now, after taking action right, you receive a reward and go into say state 2. And once you go into state 2, you again use epsilon greedy policy to decide which action you will take in next step in this state. So suppose it's again action right. Uh, yeah, let's say it's action right. Epsilon greedy policy. Okay. Now you don't take that action. You just currently you don't take it. You will take it later. But now you will use this information to update your current STAT. So again, I will summarize. So you use epsilon greedy policy in state S1 to determine to select an action, take that action, go to S2, collect a reward, and then again use epsilon greedy policy to select next action. Now, once you have these two information, ST plus 1, AT plus 1, and ST and AT, you will use this information to update your current STAT. Sorry about that. Your current STAT. Once you have updated, so the this is the equation for that. So in this case, it will be 6 plus, if alpha is let's say 0.1, so 6 plus 0.1, the reward is -1, so -1 plus gamma, let's say if it's 1, times 9 minus 6. So 3 minus 1, so it will be 6.2 in this case. So 6 plus 0.1 times -1 plus 9 minus 6. So this is how SARSA 0 method works. You use epsilon greedy policy to select action for both states, and then use the next state action pair's current estimate of action value to update your current estimate of STAT, the current state action pair, and so on. Yeah, so this is like a graphical representation. Again, epsilon greedy policy, you are in S0, get A0, receive R1, go into S1, again use epsilon greedy policy to decide A1, and then use this to update this, and so on. Same thing. And in this way, you are updating the action value of each state action pair at each time step. Now the second method is sarsa max, aka q learning. uh, so the main difference between this and the last one is how you choose the estimate of next state action pair. So I will go step by step. So you are in state 1. You use epsilon greedy policy to decide a1. Let's say again it's action right in state 1. Now instead of using epsilon greedy policy to decide next state's action, you use greedy policy. That is, you select that action which has maximum action value given state 2. So if you are in state 2, which action gives you max action value is action right. So you use this plus 9 again, and then you plug in this value into the same equation. So yeah, so this is the update equation. So again you will do 6 plus gamma whatever it is, and using the greedy policy we got 9 here minus 6, and you compute qstat and you update this value accordingly. Now the important thing is that even if you used greedy policy to determine which action value of next state to use to update your current uh, state actions pairs action value, you use epsilon greedy policy to select actual action in state 2. So once you are done updating the action value of S1 and action right, you again use epsilon greedy policy to select which action to take in state 2, and you take that action. So suppose your epsilon greedy policy gave you it given in state 2, it gave you action up, uh, and you take action up, and suppose you came back to state 1. Now to update this uh, action value, you will use greedy policy. You will to select qst plus 1 at plus 1, you will use the greedy policy, which will give you plus 7. Once you have updated this using this as qst plus 1 at plus 1, again in this state you will use epsilon greedy policy to select your next action. So summary is, you select actions using epsilon greedy policy, but you use greedy policy to decide what your q st plus 1 and at plus 1 will be. Once you have updated your current estimate using q st plus 1 at plus 1, you have to take next action in this state. So that action will again depend on your epsilon greedy policy. All right, this is the update equation. Now expected sarsa. Uh, you might have noticed expected, you will be taking some expectations. So what happens is, again when you are in state 1, epsilon greedy policy tells you to select action right. So that you select this action right, and you go to state 2, receive a reward. Now you want to update this uh, action value. So in expected sarsa, you will take expectations of all these action values for the next state, and use that expectation as q s t plus 1 at plus 1. So how do you take expectations of this? So based on your epsilon, so you determine, based on your epsilon, you determine what is the probability of selecting each of these actions. And once you get the probability of uh, selecting each of these actions, you take a weighted sum of all these state action of all these action values, and that weighted sum is your new QST plus 1 AT plus 1. So for example, your epsilon is zero point 0.4. Okay, so 1 minus epsilon is zero point 0.6. So the greedy policy, under greedy policy, this uh, action right in state 2 has probability of zero point 0.6, and under epsilon policy uh, they have probability of zero point 0.1, zero point 0.1, zero point 0.1, and zero point 0.1. So the total probability for taking this action right in S2 is zero point 0.6 plus zero point 0.1, whereas these three actions have zero point 0.1, zero point 0.1, zero point 0.1 probability. So your QST plus 1, AT plus 1 will be zero point 0.1 times this plus zero point 0.1 times this plus zero point 0.1 times this plus zero point 0.7 times this. And that is your QST plus 1, AT plus 1. You plug that value in here. So this is what I discussed until now. Sum of the product of probabilities and the action values. Once you plug that in here, it's the same procedure again, and you update your current state, current action value of this state action pair. Once you have done this, again, when you select your next action in given S2, given in this state, you use epsilon greedy policy to go to next state S3. So, so for all the three methods that I discussed, while selecting actions, you always use epsilon greedy policy while selecting actual actions to take. But to select a, a state action pair to be used as the action value QST plus 1, AT plus 1, they have different ways. And that's what we discussed right now. Uh, I will discuss all these three methods again using the quiz in the lesson, and then it will be clearer. Yeah, again, they differ only in the way QST-AT is updated, and only in the way QST plus 1, AT plus 1 is determined. And action is always selected based on epsilon greedy policy. So the action to take being in current state and going into next state is always selected using epsilon greedy policy. It's very important. Cool. So I will discuss using a quiz problem. So this is the same. I think we had, yes, same grade wall example as we had in MC methods lesson, the Monte Carlo methods lesson. This is the current estimate of the Q table. This is the current Q table, and the agent was in state 1. He selected action right. He got a reward of -1. He went into state 2, and again, using epsilon greedy policy, he chose action right, being in state 2. So how do we update QS1A1 based on the last three SARSA methods that we just discussed? SARSA 0, very easy. 6, that is the current estimate, plus alpha, let's say alpha is 0.1. So alpha times R2, that is this, -1, plus gamma, let's say gamma is 1. So 1 times 8. Now, in after going to state 2 and using epsilon greedy policy, the agent again selects action right. So that's why we use this state and action pairs. This state and action pairs action value 8 to update QS1A1. So that's why we use 8 here minus the current estimate, and that gives you 6.1. So the new estimate of this action value is 6.1 using SARSA 0 method. Sometimes it's also called just the SARSA method. And this is the equation in case you want to take a look at it later. Now, SARSA max or Q learning. Uh, Agent is in state 1, takes action right using epsilon greedy policy, gets reward of -1, lands in state 2, and again epsilon greedy policy, uh, using that policy selects action right. Okay, actions are selected using action right, using epsilon greedy policy. But then how do we update this? What action value should I use from these? Which state action pairs action value should I use to update this? Is you decide that based on greedy policy. So the greedy policy tells me that I should select +9, that is action left, to sorry, plus the action value of state 2 and action left to update the current estimate of this state action pair. That's what greedy policy tells me. So that's what I do. I use 6 plus alpha times reward plus gamma times 9 minus 6, and that gives me 6.2. So as you can see here, this is updating faster than SARSA 0, 6.1, and this is updating faster than SARSA method, SARSA 0 method, 6.1. The only difference being the way we select which action value to use to update your current estimate, which action value from next state to use to update your current estimate. Actions are always selected using the actual actions to be taken are always selected using the epsilon greedy policy. Very important. Now let's look into expected SARSA. Let's say epsilon is 0.4. So the probability of selecting greedy policy, that is 9, is 0.6, that is 1 minus epsilon, plus zero point 0.1, because there are 4 actions and each will get equal probability under this randomization. So 0 0.1, 0 0.1, 0 0.1, 0 0.1. So for for this state action pair, it's 0.7. For all others is 0 0.1, 0 0.1, and 0.1 each. So this is all the same, alpha times -1 plus gamma. And then here is where the main computation is. You use 0.7 times 9, and then 0.1 plus 0.1 plus 0.1 for other action values, -6 as usual, and it gives you 6.16 as the new estimate of this state action pair. So this is like in the middle bit of SARSA 0 and SARSA max. So this moves faster than SARSA, slower than SARSA max. If you want to implement this in the in your codes, you just use dot product. So you get a vector of these probabilities, and you have a vector of these action values, and you take dot product, and that will do the job for you. You will know when you go through the coding. You will figure that. You will find that out. Okay. So I discussed all the 3 methods, and we also discussed using the quiz. Now there are some minor improvements suggested in the lesson. One of that is optimism. So how do you initialize the Q table? So there was a paper published in 2002. You can check out this paper, and they said that if you initialize Q table to very large values, very optimistic values, it improves the performance. Uh, you converge to an optimal action value function and subsequently optimal policy faster, better. That's what their finding was. I encourage you to read this paper. This is one of the examples. So if all the possible rewards that the agent can receive are negative. So same here in this example, if you all the possible rewards that you are getting are negative, initialize q to 0 so that the agent avoids getting negative reward. So if you don't initialize it to 0, the agent will try to maximize or try to um, be less non-negative, try to be less negative. But if you initialize them to 0, it will be even better. It will be even faster. Yeah. Clear. So go ahead and read this paper. You will understand it better. Okay. So what are the similarities and differences in these three methods? So first of all three methods eventually converge to the optimal action value function, no matter which method you use. Eventually, they will give you an optimal action value function given that the epsilon decays as per this GLIE condition. GLIE you saw in Monte Carlo methods is that greedy in the limit with infinite exploration. So what this means is that you select a very high epsilon at first, probably 1, and then decay epsilon gradually, so that there is more exploration at first, and then later it's more exploitation. So high exploration in the beginning and more exploitation in the end. That's what GLI is. So this condition has to match, and alpha is sufficiently small. So the update step, how 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 much increment, how what fraction of increment you use to update your current estimate should be sufficiently small. I think zero point 0.1 is a sufficiently small number. Um, yeah. So what are the differences? Now, SARSA 0 and expected SARSA are on policy methods. So what does on policy mean? Is that your your way of selecting action, next action given a state, and your way of updating your Q value are the same. You're using the same epsilon gray policy to do that. And that's true. For SARSA as well as expected SARSA, you rely on epsilon grady policy for both. Off policy is that you use one method to select next action. So SARSA Max uses epsilon grady policy to select action, but you use another method to update your Q value. That's the greedy policy, right? So this is the difference, and it has been seen, observed that on policy methods have better online performance than off policy. Theoretically, this is what they say, but it depends on what environment you are using. It depends on your environment, what task you are using. It depends on that. Sometimes off policy methods do better than on policy, but it depends on the task. And expected SARSA does better than SARSA. So if you if on policy generally does better than off policy, and amongst on policy methods, expected SARSA does better than SARSA 0. Again, this is the keyword generally, but again it depends on the environment, the task that you're using, that you're working on. Right. So for more information, you can read chapter 6 of this book, Reinforcement Learning by Sutton and Bartow. This is a free book and it's an optional reading, but it's good to read this chapter. It helped me reading this book, going through the lessons and reading the chapters in this book was very useful to me, and it will be useful to you as well. And now I'll show you where you can find this book in our um, Udacity platform. So one second. Okay, so this is your platform. You go to this lesson, and the very first lesson on introduction, you will see this lesson covers material in chapter 6, and this is the link for the textbook. So when you click on this link, it will open in another tab in your browser, and it will load this book, reinforcement learning. I'm sure many of you have already checked out this book and downloaded it. If not, go ahead and download it. It's free and it's very useful. And check out chapter 6 in this book, and even other chapters for other lessons as well. Very useful. Okay. So yeah, so in this webinar we learned about the differences between MC methods and TD methods. I also showed you the high variance, low bias versus low variance, high bias difference in them and why it is. You don't need that concept now, but for later on, for your later lessons, you will need it. Uh, but we also saw other differences that depends on the whole episode to be sampled, and this does not. There are three ways: SARSA 0, SARSA max, expected SARSA. We also went through the quiz problem to differentiate and to see what's the difference in these three methods to compute or to update the current estimate of some action value. Optimistic initialization, very important, improves the performance. And then we saw some similarities and differences of these three temporal difference methods. Uh, I will. I'm going to show you that one small. There's a optional quiz problem in your lesson. So I'll just give you a brief information about it. So just give me 1 second. Okay. So in your lesson, if you scroll down when you finish the whole lesson, number 16, check your understanding. So I'm sure you have tried other quizzes in this lesson, but I encourage you to check these as well. Here is an agent, and here is an environment. Read the Go ahead and read the description. And initially, all the action values are 0. The Q table is 0, and there are some couple of questions uh, about computing the the update for a current estimate of a given state action pair. So go through this, and the agent uses Q learning, SARSA Max, to update its estimate. Um so please try this quiz. The important thing to remember is that you update you use greedy policy in uh, in Q learning, but to select action you use the epsilon greedy policy. So that's the important thing to remember here. Ignore this. This is just for me because I'm not the student anymore. But yeah, you should see a quiz here and quiz here, and you will have to type in some numbers, the updated estimate. So it's a good practice for concept wise to clear your concepts. It's good because it can be confusing that why selecting actions is epsilon greedy, but selecting the Q ST plus one, AT plus one, you use greedy policy. It can be a little confusing. So this exercise will clear that out for you. Also, I wanted to discuss quickly about this the coding exercise in this lesson. And again, if you have any questions, you can shoot send the questions to me on Slack direct or direct message me. So this lesson discusses this lesson implements all the three methods on the same environment. It's a cliff walking environment. So go ahead and explore this lesson in gym.make. So in case you are new to open AI gym environment, this is a good practice. These are some commands to know what action spaces are in this environment, what are the observation spaces. Okay, and there are only two main functions that you need to compute, two or three main functions to solve this notebook. Wo- So I will quickly show you the solution notebook. I won't spoil much. Uh, yeah, so one is updating uh, update function q that you will have to write, and another one is for epsilon greedy probability. So this epsilon greedy probability function as well as the update q function, you can use those two for all the three methods, and the only difference is how you implement that update q function. So you might have seen the same this structure of training your environment in the MC control methods as well. So it's a similar structure. You you select a random state at first, and then based on a policy you select action and etc etc. You update your queue table. So the difference will be here for all the three methods. How how they differ. These are for plotting, some functions for plotting. For Q learning, again, the difference will be here. Here we use NP max, obviously. And for expected SARSA, as I told you in the seminar, you just use the dot product of the policy, the probability vector and the action value vector. Rest is just for saving the scores and taking average and plotting them and etc. So so in case you have trouble getting started or you don't know where to start or how to what to code, you're most welcome to look into the solution notebook. Okay, explore it, try to understand each code, each module, how it is used, and then try to implement it on your own without looking into the solution file. Understand each, because that's what I did. Understand what this function does, what this code does, and then implement it yourself. That's how you will learn, and it will help you for your projects as well. So I guess that's it uh, for today's webinar. Um if you have any questions, you can ask me on Slack anytime. I'm always available. Uh, and you can direct message me. Uh, there is also the taxi mini project. It's not a submission project. You don't have to submit it to graduate, but it's a good application of all the concepts that you learned until now. And you might see that you use same functions for the different coding exercises by just tweaking them slightly. You will notice that too. So that's how you learn, you implement yourself. And if you have any questions, any problems, you can ask me anytime. So I will wait for your questions, uh, and then we can end this webinar. Okay, seems like uh, currently there are no questions, but feel free to watch the recording of this webinar as many times as possible. If you have any conceptual problems, any problems with the workspace, the coding exercise, quizzes, anything, just direct message me on Slack and I will get back to you as soon as possible. So thank you for watching this webinar and have a nice day. Bye.